Things are off. You can turn them back on now for the next hour. So this is actually installment number 1 of my eventual complete sermon on in DraperBayes of hypothesis testing. And that implies that I'll have more later. I think I can manage to hold down the foaming in my mouth to only 2 such episodes, but I do have more to say on the subject than I'm going to say here. And it sounds like we might be failing again somehow. The setup is a random of new versus old. I can do that. Randomized controlled trial of a new treatment versus an old one. We have n human subjects randomized. Let's say n is even, randomized n over 2 to the old treatment and n over 2 to the new, and n is some fairly large number. This applies to lots of things that are being done here in the Valley. This is the basic paradigm for A/B testing. It's also the basic paradigm for clinical trials. Is it working now?
I don't want
Okay.
to try it.
It's true. It could be too much feedback. Let's try now and see if that's. So let's try anyway. The literature on this is vast because people have been doing clinical trials for many decades more than people in Silicon Valley were doing A/B trials, but lots of things written about this. And the unknown here, I'm going to call it theta as usual. The unknown is the mean difference, new minus old, on the most important outcome of interest to you. Might be money, might be number of clicks, things like that. And let us scale this outcome without loss of generality so that large values are better than small. That automatically comes if they were thinking of money, for instance. And theta is the mean difference, new minus old, in the population, script P, of subjects that you would judge exchangeable with those in the trial. So in other words, you could just look and see what the difference is. Treatment bar minus control bar, y bar t minus y bar c, that would be a good estimate of theta, but you wouldn't have theta yet because you're trying to generalize outward to the population. So this is like imagining that the little n trial subjects were randomly sampled from P. And of course, this is typically not how subjects are actually enlisted in trials. In the clinical trials world, people do their best to get a process of arriving at the patients, the experimental subjects, in a way that's as close as possible to like a random sample from the population of everybody with that particular condition, for instance. But it's never really literally done that way. And as I think I may have told you before, there are egregious examples where people get 9 patients at one hospital and randomize them into 3 groups of 3, and they find a so-called statistically significant difference, and they write about it in the New England Journal of Medicine, which is a good place to publish things, as if they now knew the answer for everybody with that particular condition, which is, of course, really silly. So the issue of how to appropriately generalize outward from the subjects in the experiment is something that involves thinking about what is the scope of your exchangeability judgment, right? Who are these people in the experiment, and what is the broadest scope of valid generalizability away from them? And if you are able to think of the subjects as like randomly sampled from script P, and then, of course, you randomize them to new or old, then theta has a causal interpretation, a cause and effect interpretation, namely as the mean improvement per person caused by receiving the new treatment instead of the old. So in the world of causality and cause and effect, we're trying to estimate the effect of a cause rather than the other way around. We know what the putative cause is, namely, did you get the treatment or did you get the control? And we're trying to estimate the effect of a cause, not to try to do the harder thing of estimating the cause of an observed effect. Now, we've seen by now that there are 2 frequentist schools of inference that developed and burgeoned in the 20th century. You got Fisher on the one hand, and you got Neyman on the other hand. And so here's Fisher's story. Fisher's story has 2 parts. He has told us, as you've seen in component A, I've emphasized it, about how to construct good point and interval estimates of theta based on the likelihood function. So that's Fisher, getting you good point and interval estimates, as long as n is large and you don't have much prior information external to the data set. Then part B, which I have not emphasized for reasons that you'll see when I finish this little sermon, he also emphasized summarizing the evidence against a null hypothesis that claims that theta is exactly equal to 0 in the population. And he was the one who promoted the idea of a p-value as a way of summarizing the strength of evidence against a null hypothesis. You may recall that the p-value is rather convolutely defined as the chance, comma, if the null is true, comma, of getting data as extreme as, comma, or more extreme than, comma, what you got. So that's a mouthful, but that's what a p-value stands for. You have to think about how the data should have looked if theta really were exactly 0, and then you construct a measure of the distance between what you actually saw in the data and what you would have expected to see if the null had been true, and you work out the chance, if the null is true, of getting data as unusual as that or even more unusual. And that's his p-value. He was the one who emphasized p-values. He wasn't the only one testing null hypotheses. That was, Neyman did that also. But Fisher was especially fond of testing what you can call point null hypotheses, like this one here, that theta is exactly equal to 0. Now, it's not written on this stuff, and I will write about it more in later stuff, but if theta is the mean improvement, new versus old, on something that lives continuously on the number line, then it's kind of stupid to test whether theta is exactly 0 or not, because you know it's not exactly 0. It lives continuously on the number line. It can't be exactly 0. If you thought it might be exactly 0 and also exactly every other number on the number line, then you end up with probability there's too much probability, right? A literal interpretation of theta, a null hypothesis, a sharp null hypothesis like theta, or point null, people sometimes call it, theta exactly equals 0, is stupid on its face because we know theta is not exactly 0. So maybe what people really mean is that theta is around 0, where the around 0 part is governed by a kind of indifference region. If theta were this small or smaller, it's too small to matter from a practical point of view. And in that case, you end up running a different hypothesis test and getting a different p-value than what Fisher had in mind. So one of my beefs against Fisher is that he tried to get everybody excited about p-values based on sharp null hypotheses, and one of my other beefs about him is that he tried to get everybody excited about sharp null hypotheses at all, because they're usually not a good reflection of what's actually going on. Now, in competition with Fisher, we have the Neyman-Pearson approach, and it also has two parts. There's a part C, which is about testing, and there's a part D, which is about constructing a confidence interval for theta with some pre-specified confidence level, like 95%. So you take, in the expression 101 minus gamma, you take gamma equals 0.05, and you get confidence level 95%. Now, C is a much bigger mouthful in the Neyman-Pearson world. In the Fisher world, you never had to think about any alternatives to the null. Fisher's approach isn't really called hypothesis testing. Fisher's approach is called significance testing. And in Fisher's approach, there aren't any alternatives. There's only the null, that theta is exactly 0, and then you work out a measure of how badly the data fit to that particular null. Neyman and Pearson said no, and Neyman and Pearson were right about this. Neyman and Pearson said no. The only way to judge the plausibility of one hypothesis is against another one. And so you have to be able to say, what is the alternative that you're interested in? And in their case, they were interested when the null was sharp, theta equals 0, against an alternative that just says that theta is some number other than 0. And again, just thinking about it from the point of view of the quantity theta being continuous, in some sense, we already know that the alternative hypothesis is right, because theta can't be exactly 0, so it has to be some number other than 0. So there's already something funny about this from a logical point of view. But anyway, the way Neyman and Pearson thought about it was quite different, because they explicitly brought the alternative hypothesis in. They tried to develop rules for how you should look at the data and either, quote, reject the null hypothesis or fail to reject it. And these rules are as a function of sample size, and they're also as a function of the actual data vector values. And you're supposed to reject the null with a pre-specified so-called type 1 error probability. Alpha is the usual name given to that. And that's the chance of incorrectly rejecting the null when it's actually true. So that's the one kind of mistake you could make from their point of view. And of course, if there's two different possible hypotheses and you're thinking about all the mistakes you could make, that's only one of the two possibilities you could mistake. You could falsely reject the null, or you could falsely accept the null. They called that second kind of mistake type 2 error probability, the chance of incorrectly failing to reject the null when it was actually false. They called that beta. And their idea was that you should always set the null up so that alpha, the type 1 kind of errors, are more important than the type 2 kind of errors. And that meant that in the process of trying to make alpha and beta both small, as we've seen in the ELIZA case study, with a fixed way of extracting signal from the data, it's not possible, and a fixed sample size, little n, it's not possible to make alpha and beta both simultaneously as small as you want because of that beanbag thing I told you about before. When you try to make one of them small, it's like shoving it on one side of a beanbag chair and the other side bulges out. And so with a fixed sample size and a fixed way of processing the data, you cannot make them both small at the same time. And so Neyman and Pearson said, we're going to pretend that you always set your null hypothesis up so that the type 1 error is more serious than the type 2 error. And that means what we tell you should do is you should pick your alpha first, and then, having chosen an alpha, you should choose your sample size so that the beta is as small as you want against some particular alternative positive value, theta 1, for example. And this is equivalent to, they invented a concept called power, which is 1 minus beta. This is equivalent to choosing n so that the power, 1 minus beta of the test, is not less than some pre-specified threshold. So you have to pick out some alternative value, theta 1, that you want to be pretty sure of getting right if that's really what's going on. And their recipe is first fix alpha at some small value, and then solve for n to see how big n needs to be in order to get the beta to be small also, or equivalently the power to be 1 minus beta to be large at that particular alternative theta 1. Very complicated way to draw inference about the world. Now, in practice, a combined frequentist approach has somehow evolved in which randomized trials are often designed from the Neyman-Pearson point of view. So you make a power calculation to decide how much data to get. And that's corresponding to using idea C from the Neyman-Pearson camp, but then summarizing the data evidence with Fisher's p-values. And that was using method B in Fisher's approach as measures of evidence against the null. And when you think about the world from the perspective I've been trying to share with you this week, the Bayesian story, that's an extremely perverse way of coming away from the Neyman-Pearson and Fisher framework. In fact, it's exactly picking out the wrong two possibilities. It focuses on the worst of each of the Neyman-Pearson and Fisher approaches. So from a Bayesian point of view, this approach perversely emphasizes the worst of both the Fisher and Neyman-Pearson schools. And it does so by failing to focus on the most scientifically relevant summary of any given trial, namely an interval estimate of theta on the scale of the most important outcome variable. In other words, the result of a hypothesis test is a probability number, a p-value. That's the wrong scale, I'm arguing in this little chapter here, on which to be judging what happened in the experiment. The right scale is the data. How much money, how much more money did eBay get by setting the website up this way than setting it up this other way? That's the right scale on which to be summarizing inferentially. P-values are a big mistake because they wander off to the wrong scale. They wander off to the probability scale, which has no direct meaning in terms of making decisions. So this is one of my rules of thumb from this course. Try hard not to wander off onto some other scale that doesn't matter as much as the scale you really care about. P-values wander off artificially onto the probability scale. When you can find a way to stay on the data scale, well, that's exactly what interval estimates do. And so Neyman's confidence intervals, when they're constructed well, and Fisher's intervals, when they're constructed well based on the maximum likelihood estimate and the information and so on, they are the right place to be because, from a Bayesian point of view, they are the best approximations the frequentists can offer to a directly Bayesian analysis. In effect, a 95% confidence interval with a large sample size is often equivalent just to what you would get by drawing the posterior distribution with diffuse prior information and picking out the 95% central part. So it's actually a way to do something from the frequentist point of view that's pretty close to the right Bayesian answer. Only, however, when n is large and the prior information is relatively weak. So it's much harder to think about, the reason for this is it's much harder to think about whether probabilities are important scientifically. So someone tells you, I've got my data in and I worked out the p-value is 0.03. And now we're all sitting around wondering, is 0.03 small enough to decide to abandon the current web page and go with the new one? It's just not the right scale on which to be thinking about that. Instead, it's much better to think about whether changes on the main outcome scale of interest are real-world relevant. We can ask myself, for instance, would it positively affect eBay's bottom line if the change to the web experience we're now studying increases the percentage of visits to the eBay web page that end in an actual sale, a non-zero sale, it increases that from 10% to 12%. Any eBay people in the room, would that be a good thing? To get the proportion of actual transactions that result in somebody buying and selling something to go up from 10% to 12%, would that be big enough to matter? That's enormous. That's enormous when you multiply that against eBay's volume. Okay, so that's the scale on which we can begin thinking about what really matters, and it's on the scale of the data. Yes. Well, and so, but at least that answer comes out on the scale that we can think about because it translates directly into behavioral choices. We're talking about on the data scale, on the money scale, and asking whether this difference is big enough to translate into something that's valuable enough to the eBay bottom line to make it worthwhile to implement the change, which itself is something that has costs, for example. So if you were doing a straight up cost benefit analysis, you know something about how much it costs to change the web experience over, and you know something about how much you gain, what's the benefit from this sort of thing. The benefit could be really small. It could change that 10% number to 10.006, in which case that difference is not big enough to matter from a practical point of view. And even if it turned out to be statistically significant because we have 12 million observations in each of the groups, it's still not worth paying any attention to because it's not large enough in practical terms. And so the p-value lets us down on that front also. The p-value has no information in it about whether the difference is large enough in practical terms to actually help us make a choice. It's just not the right way to summarize the data. Well, the whole idea of trying to learn about the world from a statistical point of view is that when you're trying to say something about a population, it's either impractical or too costly for you to do a complete census of that whole population, and instead you decide to try to take a good random sample from that population and then base your conclusions on what you see in the good random sample. And it's just a part of the nature of random sampling that every now and then a good random sampling method, namely one that generally does produce quite good random samples, every now and then produces a bad one. And you just have to accept that as part of the process of learning about the world in that way. If you really want to know what theta is, you have to create a big box with all the population values in it and dump the whole box out and do a complete census. And no one ever can do that. It's just too expensive, or maybe the actual population is too vague to even pin down. Who are these people exactly? Well, they're future eBay viewers to the website, and we haven't even seen them yet because we're trying to figure out what will happen if we do this tomorrow and then wait and see how things are going over the next 6 months, let's say. That's another kind of problem that can arise. That's a situation where the difference is large in practical terms, but not in statistical terms. That will never happen at eBay because we always have 12 million observations in each group. And so that will never happen. The other kind of mistake is the one that might happen. We might end up concluding that something was statistically significant because we have so much data, and yet the difference is too small to actually matter. That's the other kind of mistake that can happen when you... what I'm basically talking about is a topic that I think I should create a unit on in here. Someone asked about this the very first day, namely all this stuff about you've got n observations, and so the question is, well, how did you decide on what the value of n was? At design time, you had to decide this. And at eBay, for example, that decision corresponds to deciding how long to run the experiment. If you only run it for 1 week instead of 2 weeks, that cuts the expected sample size in half, for example, roughly. So how do you decide on how big n is? And essentially the rule, and I'll write up some slides about this, is to think about how big a difference would have to be in order for it to be large enough to be practically meaningful. And then try to make sure you have enough data to have a good chance of showing that differences of that order of magnitude are real rather than just artifacts of unlucky random sampling. So you try to make the concept of practical significance and the concept of statistical significance come into rough correspondence with each other. And that's how you do a sample size calculation. By statistical significance, I mean the usual thing. You're in the world trying to separate signal from noise, and you have a rule that's based upon noisy data. And so every now and then the rule might inadvertently say that you had signal when you didn't, and otherwise it might inadvertently say you don't have signal when you do. That corresponds to Mr. Neyman's type 1 and type 2 errors, right? And so statistically significant is like saying, this is Fisher's way of thinking about it, if there really were no difference, how often would you be fooled into thinking there was a difference anyway by having a difference show up in the data that is really big? And that's the sort of thing he thinks about. When that chance is rather small, he would say, you have a statistically significant finding, you can go out and publish it now. And unfortunately, in Fisher's world, he never really thought hard about practical significance. I don't really know why. I don't think he ever wrote about experimental design in terms of how much data you should get. I've never seen any writings from Fisher on that point. I think as I told you, he was working at an agricultural research station in Rothamsted, and I think they were basically forced to use whatever sample sizes they could based upon how much land they could get to plant the crops on. They just couldn't have a sample size any bigger than blah blah, because that's how many potato plants you could put on this many acres of land. So maybe it never occurred to him, but we of course have to worry about this, and I will talk about it more later. All right, so here's a standard example. I run my randomized controlled experiment, and the p-value comes out 0.02, which everybody has told me that's small enough to publish. But can I tell, if all I tell you that the p-value is 0.02, can I tell from this whether the difference I found is meaningful in the real world? Well, let's find out. The standard story behind a two-tailed test of the sharp null that theta is 0 against the fuzzy alternative that theta is not 0, it turns out you can work backwards from the p-value of 0.02 to, in large samples, to figure out that the standard test statistic would follow a standard normals distribution, so I'll call it a z, and it would have the form average of the new outcome minus average of the old on the outcome scale over the estimated standard error of that difference. And I can work out that the value of that ratio that gave rise to p equals 0.02 was either plus 2.3 or minus 2.3. And in fact, that's all I'm able to conclude on the basis of being told that p was 0.02 and the alternative was looking for evidence either on the high side of 0 or on the low side by using the alternative theta is not equal to 0. Well, this is disastrous because just looking at the p-value, I can't even tell from the p-value whether the new treatment was better or worse than the old one. I can't even tell whether the actual z number was plus 2.3 or minus 2.3 because it's a two-tailed p-value. When you're looking for evidence on either side, it's got to be one of those things that everybody calls a two-tailed p-value. That's a disaster. Moreover, the thing I really want to know to judge the practical significance of this finding is the numerator of that ratio, namely new bar minus old bar. That tells me how much actually increased revenue I would have if I projected it out over blah, blah, many users and so on. And the thing that tells me whether the difference is large in statistical terms is the denominator of that fraction, the standard error, which says, I think that the true theta is around new bar minus old bar, give or take standard error of new bar minus old bar. So that tells me something about whether theta differs from the actual estimated theta differs enough from 0 to regard it as probably signal or maybe could be noise. That's the idea of statistical significance. So I want the numerator to tell whether the difference is large in practical terms. I want the denominator to tell if the difference is large in statistical terms. And if all someone gives me is the fraction, can I reconstruct both the numerator and the denominator from it? No. If I just told you that the z ratio was either plus 2.3 or minus 2.3, and maybe even I put you out of your misery and said that the z ratio was plus 2.3, so that we do know that the new was better than the old, at least, in the data, you can't tell when you're told the value of a ratio, you can't tell what the numerator and denominator were of that ratio, because someone else could take those two numbers that were really there and multiply them both by 6, and you would have the same ratio, right? So the so-called z statistic, which people use to get the p-value, has taken precisely the two pieces of information that you want to know separately and combined them into a one-dimensional summary which loses both of those pieces of information. Therefore, it must be a really terrible way to summarize the data. As a single numerical summary of what's going on, you have lost the two things you care about because you've allowed someone to combine them into a fraction which does not allow you to reconstruct what they were. So the p-value has thrown away crucial information by specifying only the ratio of items 2 and 3 here, rather than their separate and separately important values. So what's better than that? If I have to work out the numerator and denominator separately to pin down both the practical and statistical significance of what happened, both of which are key scientific summaries, then what's the point of calculating the p-value at all? Why don't I just keep the numerator and denominator separately and think about them that way? And that's basically what I'm arguing. If someone reports for you the numerator and someone reports for you the denominator, you can take the denominator and multiply it by 2 and go numerator plus or minus 2 denominators, and you've got an approximate interval, which is like an approximate Pasteur distribution, and that's what you want, because the answer comes out on the scale of the data. So why not dispense with it altogether and go directly to the 95% interval estimate, numerator plus or minus twice denominator? That's got to be a more informative summary. If someone offers you a p-value, it's never enough information. And if they offer you the interval instead, you can work out the p-value. If you're a person who likes to look at p-values, if you give me the interval, I can work backwards to find out what your p-value is. That's fine. So the interval is actually where it's at. The p-value has no information of its useful information at all. If all you get is the ratio of those two numbers, you really need to know the numerator and denominator separately. So for me, as I've said already, this is a large sample approximation to the Bayesian solution, namely to look at the Pasteur. When prior information is diffuse, the central 95% part of it's going to look a lot like that interval by Bernstein von Mises. So for me, this argument demolishes the use of p-values in inference. It's just, don't do it. It's not helpful. Although I will make better use of the argument that is at the core of Fisher's p-value later on, when we are trying to check diagnostically whether the data could have come from a particular statistical model, which is part of the process of deciding whether the model you have in front of you is good enough to stop looking for a better one. And that does turn out to be a situation where something like Fisher's p-value is the only way forward. So there is one part of the Bayesian world in which Fisher's p-values make good sense, and it is not inference, and it is not prediction. It's the part of inference and prediction that has to do with checking to see whether your tentative current model is okay or not. So it's kind of buried in the very middle, like the part that goes on under the hood or inside the box of this black box. We have a model, and we have to check and see whether the model is any good. Then Fisher's p-value idea does turn out to have some value, and I'll show you that later on. But if all you're trying to do is to take a data set and summarize inferentially what you can learn from it, the p-value tells you nothing of interest to you. And everything that's of interest to you is found by taking the numerator and the denominator that go into the z ratio that leads to the p-value and using them to build an interval. And yes, please. Well, but if I know the interval, then I already know whether the p-value is less than 5% or not by checking to see whether the 95% interval includes 0 or not. Those two things are... Well, but actually, if we're comparing to 0, then all we have to do is look at the interval and see if both numbers in it are either positive or both numbers are negative, right? I mean, that's it. It's not hard. It's true, but the two numbers tell you the two things you need to know. They tell you whether the difference is large in statistical terms by comparing the interval with 0, and they tell you whether the difference is large in practical terms by looking at the interval and comparing it with 0 to see if it's far enough away from 0 that it actually creates a useful net gain to your bottom line, for instance, or whatever it is you're trying to optimize on. Uh-huh. Yes. Yes. This is a complication that I would like to talk about later on. His perspective is that of being in a clinical trial where there's always a main comparison to be made. For example, on average, was the treatment better than the control? But then you almost always want to do subgroup analyses. You want to say, was it better on average than control for black people? Was it better for white people? Was it better for old people? Was it better for young people? Was it better for blah, blah? You can see how that would go. And it's a sad fact about clinical trials that if you do the power calculation to figure out how much data you should have for the main comparison, you will often find that you don't have enough data to do a quite reliable job simultaneously on all those little sub-comparisons as well. And moreover, many of the sub-comparisons that are interesting turn out to show up in the data that you didn't even know were going to be there. And so you have to decide, you have to have a good way of separating signal from noise when the actual signal was something you didn't anticipate. And so, yes, I will talk about that later. However, the people at the FDA might or might not like my bottom line, which is that all of the stuff that the FDA does is in keeping with the Neyman Pearson story, which is very, very, very terrified of making false positive mistakes, of saying that a treatment is effective when it's not. But if you think about a treatment like a drug treatment that would serve as a vaccine against HIV, and you actually had a vaccine that worked, and you end up concluding that it didn't work because you were underpowered, for example, in your study, that's a false negative. That has very strong real-world consequences right along with the false positives. And if the FDA did a better job of balancing false negatives against false positives, they would move back toward an inferential framework in which you don't have to do so much adjustment for multiple comparisons. Because in effect, the way multiple comparisons work, you have to you try to protect yourself against the possibility of false positives along many different dimensions in your data set, including those that you didn't even think about before you got the data. And so, naturally enough, to do that, if you're going to reason on the interval scale, which is where I believe you should be reasoning, you should take your intervals that would not have arisen from multiple comparisons logic and make them wider, because that hedges against the possibility that you might make a wrong conclusion because you're trying to draw lots of conclusions at the same time. But that's the process of making the intervals wider based upon a fear of false positives. But if you instill in the machinery an opposite reaction that involves a fear of false negatives, because it's a very bad thing for humanity to leave a working HIV vaccine on the table and not point out that it works, for example, every moment you spend working to be worried about false negatives takes those intervals that got wider and makes them narrower again. And so if you're in a situation where the false positive downside is about the same magnitude as the false negative downside in the real world, then actually constructing your intervals without doing any multiple comparisons adjustments at all is a better answer to your problem than one in which you're only terrified about false positives. So I'll have more to say about that later. That's an interesting and touchy subject. The null value. Absent any other information and having the prior been brought in appropriately to bring in all information external, the Bayesian conclusion would be the value of 0 is supported by the data because it's inside the central 95% interval, except that the Bayesian would also say, why are you using 95% rather than some other number? The 95% interval was chosen based upon a fear of 5% false positives. And where did you get your 5% number? Would be one Bayesian response. If you're trying to make a decision, namely, should we take this drug to the next phase in phase 2, 3, or 4 clinical trials, for example, or should we actually implement this treatment out in the world, decisions like that, then I'm going to argue about this later on for you as well. The standard inferential machinery of just building intervals and seeing if 0 is in them or not, or looking at p-values and seeing if they're small, may well not be the right decision because, it doesn't necessarily trade off properly the false positive and false negative mistakes. But if you buy into the 95% story, then the standard Bayesian thing would be to compute the posterior and see if 0 is in it or not. If it's not in there, you can say in the usual ways frequentists do that we have pretty strong evidence that theta is not 0, and if theta is in the interval, we say the data are inconclusive on this point. It could well be 0. Now, there are other Bayesians who would say the following, and I will get into this later on. There are some problems, a rare set of problems, in which theta really could exactly be 0. And here's an example. I used to work at Rand in Southern California, and then I moved to UCLA for a while before going to England and then coming to Santa Cruz. And I used to like to drink tea, in those days, and I used to make my own tea. But then when I got to UCLA, somehow I didn't have any tea making machinery. And so for a while, I got my tea by going down to this machine that served vague, unidentified cups of brown liquid and called it tea. And the coffee looked the same as the tea, and not entirely unlike tea. Yes, that's right. And the coffee looked and tasted the same, pretty much, right? And I will interrupt my story with an Abraham Lincoln joke for you if you've never heard this before. Lincoln was out on the hustings, campaigning, and he came to some inn at the end of the day, and they put a cup of indistinguishable brown liquid in front of him. He took a sip, and he said to the person running the place, he said, "If this is tea, bring me coffee. If this is coffee, bring me tea." So that's the kind of stuff you got out of this machine. Outside of the machine, pasted on the front of it, was a little sticker that said, "You might be lucky. A small percentage of the time, we give you the cup of tea for free." In other words, the machine gives you your quarter back or whatever you were paying and gives you the tea anyway. Well, okay, that seemed interesting, and so I went along and I kept some track of free cups of tea or not, and I went through 78 straight cups of tea with no free cup. So I have a Bernoulli process unfolding with 78 zeros in a row, and it occurred to me that some wise asses in the company that made this machine might have decided that it was cheaper just to put that label on the front of the machine with no actual randomization device inside than it was to put a randomization device inside. And so this is a situation where you are really testing a sharp null hypothesis. Theta is exactly equal to 0 in a conditionally IID Bernoulli sequence versus the alternative that theta is some small positive number. And the reason that theta is exactly equal to 0 is a legitimate null hypothesis is that it corresponds to a physically different state of nature. There either is no randomization mechanism in there or there is one. So that's, in 30 years of applied work, that's the only problem I have ever come across in which it was legitimate to test a sharp null point hypothesis. Every other situation I've ever worked on, when someone said they wanted to test where theta was equal to 0 or not, I would say, don't you really mean, is theta just close to 0? Isn't your uncertainty about theta continuous around 0? In which case, we shouldn't be testing the sharp null at all. But Bayesians would say the following thing. There's a narrative in which you say, suppose you're working on one of those very rare problems in which theta really could be exactly 0. Then in your prior distribution, you have to put some point mass at 0, right? To end up with the posterior distribution having point mass on 0, the prior has to have point mass on 0 by Cromwell's rule, right? And so you have to put down a weird-looking prior that has a point mass at 0 and the rest of the mass spread out on the interval from 0 to 1 in my problem, right? Well, how much mass should you put on theta equals 0? In other words, how much prior probability should you give to the null? And standard knee-jerk Bayesian analysis of this problem, with which I do not subscribe, is that and this comes from a wonderful man named Harold Jeffreys, who was a great astronomer and Bayesian statistician back in the 1930s and 40s. Harold Jeffreys said, the only, quote, objective choice is that the prior probability on 0 should be a half. Now, I don't think in my T problem that I have that much prior mass on a half, because that corresponds to them committing some kind of fraud on the public, right? I mean, and they could be, if you were able to show that their machines did have no randomization mechanism in them, they could pay a big fine. And so I don't think theta is exactly, rather the prior mass on theta is equal 0 should be a half. But all the rest of these Bayesians, ever since Jeffreys, have taken as an absolute constant of nature that theta, the prior, should have point mass 0.5 right on 0. But if you look at the problem in the right way, that's like trying to put down something that's an approximate continuous prior on theta that has a tremendous amount of mass right on the null. And in effect, what you're doing is you're creating a posterior that loads a lot of skepticism about the alternative into it, because you put so much prior mass on the null. And so there's all these papers written by people like Jim Berger and these other people that say, oh, p-values are silly because they exaggerate how strong the evidence is in favor of the alternative. And that's because he's always making calculations where he puts point mass 1/2 on the theta equals 0. And no wonder he gets measures of evidence that are weaker than that against the null, because he's just loaded a tremendous amount of prior probability right on the null. And how could anybody call that objective, by the way? If you were trying to be even-handed, that turns out to be the opposite of even-handed. You put a tremendous amount of prior mass on one particular story, and you spread out the other half across a countable infinity, an uncountable infinity of the other stories. I myself don't have an omnibus solution to the point null hypothesis from a Bayesian point of view. It has to involve putting a point mass at 0, and you have to end up calculating a Bayes factor between that and that null story and the alternative. But I don't think it's cut and dried that you should always put a half there. In fact, I think it's very much not cut and dried. You should put a half there. So we'll talk more about this later. There is an elaborate Bayesian narrative about how to test sharp null point hypotheses, which I think is largely irrelevant because almost all the problems you're really working on, the uncertainty you have about theta is inherently continuous, and you should not be putting down any kind of prior that has a point mass at a single point. That's just silly. Okay. Now, looking back at those 4 approaches to inference that I mentioned, 2 of them from Neyman and 2 from Fisher, I said that B and C were absolutely the worst possible combination, and that people should be focusing instead on A and D. But look at what A and D are. They're the same thing from 2 different points of view. Fisher says build point and interval estimates based on the likelihood function, and Neyman says construct confidence intervals. And so either way, with A and D, you're getting an interval, and that's much more like what you want to be getting. So if you're going to be a frequentist, I recommend don't pay attention to p-values. Pay attention to interval estimates on the scale that really matters to you, and compare those interval estimates with whatever null values you're interested in. The right null might not necessarily be at 0, as I mentioned before. The right null might easily be involving an indifference region around 0. So let's look at that for a second. Usually in a problem like this, this is 0, and better is this way. So if the truth is negative, you certainly don't want to go forward with this new better than old. And so this direction corresponds to new being better, for example. But there will generally be a region of the form 0, A out to A, within which if the truth really lies in there, it's not big enough from a practical point of view to be worth actually changing the way you do business and moving it to this new thing. Like I talked about before, if the old number used to be 10% and the new number is 10.006%, that when you subtract them, you get a very, very tiny region. I mean, that point falls within a kind of indifference region. So this is a sort of indifference zone. And this number is what I'll call a practical significance threshold. And so your null is really that theta is somewhere in there, or maybe that theta is less than or equal to A. So that acts like your null, that theta is less than or equal to A, against your alternative that theta is bigger than A. And for that purpose, why not just work out the Pasteur distribution and compute the Pasteur probability that theta lies in each of those regions? That's going to definitely tell you what you want to know. So I like the Fisher interval estimates, and I like the Neyman-Pearson interval estimates. They're much more in keeping with the scientifically compelling idea of staying on the data scale, but they themselves do have 2 drawbacks in relation to the Bayesian approach. They fail to incorporate relevant prior information when you have it, because they have no mechanism for doing so, and they don't necessarily work very well when the sample size is small and the resulting likelihood function is heavily skewed. Mr. Neyman has the same kind of problems because the central limit theorem won't work for him in small samples, so he can't really build an interval based on the central limit theorem. So if you're going to be a frequentist, I think you should be an interval estimate frequentist. That's got to be the right way to summarize your data if you're not going to try to bring in prior information. But why not just go ahead and do the Bayesian thing? So that's been episode 1 in my rant against hypothesis testing, and I will have an episode 2 later on. All right, so that finishes that unit. And although I have not put it on the web page yet, I realized at lunch that we might run out with time left. And so I have created for you the beginning of part 3. And let's spend the last 15 minutes looking through this. This entire unit is not going to be about good specification of Bayesian models, which is an important topic that we'll talk about later. And it's not going to be about good ways to check models. It's not going to be about any of that stuff. It's going to be about something that is even more fundamental, namely actually making Bayesian computations in settings where the conjugate story doesn't work. So we've now seen that the conjugate story is nice when you can do it, because you get closed form results and they have those nice interpretations about prior sample size and so on. But it's limited in scope to what you will see when you start doing this stuff as a real world day-to-day practice. It's limited to a fairly small set of models for which straightforward conjugate results are possible. So conjugate story has good and bad, and the bad outweighs the good. When you've got a conjugate story, by all means use it as long as your prior information can be well fitted into that framework. But otherwise, you're out of luck for the conjugate story. And this was a big limitation for the Bayesian story almost for 250 years, because people forgot what Laplace did after he died. And so over the past 10 or 15 years, the Bayesian community has rediscovered and developed an entirely new computing method, which we now call Markov chain Monte Carlo. And I will say discovered in quotes, because actually it was first figured out by physicists more than 50 years ago. I mentioned to you Metropolis and Ulam. Their paper was published in 1949, but they figured out that insight that, and here it is down on this page, anything you want to know about a probability distribution, even of arbitrarily large dimension, as long as that dimension is finite, can be learned to arbitrary accuracy by A, developing a method for making random draws from that distribution, and B, having the time and the money to get a lot of draws from that distribution. Because the more draws you get, the better. The more draws you get, the more accurately you can summarize that particular aspect of that distribution. And so you have to have a way to sample, and a way to sample fast enough that you can get enough samples in a decent amount of time to be able to solve your problem. That's going to turn out to be the big problem when we try to apply MCMC to these eBay-style data sets. I can show you a good parametric model for A/B experiments at eBay, but there's 12 million observations in each of the treatment and control groups, and the parametric model is a complicated mixture model. And if you tried to turn MCMC loose on it, you could start your computer on a Monday morning and you wouldn't have any answers back by the next Monday morning. A week of computing would produce only a very small number of iterations and not enough to get a good idea of what the posterior distribution is. So MCMC is great for small and medium-sized problems, but even learning how to do this is going to create limitations for us in the Bayesian paradigm. Some people in machine learning have tried to get around this with a technique called variational methods, Michael Jordan and other people in his camp. I will talk a little bit about that if there's interest toward the end as well. The problem with the variational guys, what the variational guys do is they create a problem that is not the same as your problem, but which they warrant is close to your problem in some sense, which they all have a hard time actually pinning down. And then they show you how to do extremely fast computations in their problem that's close to yours. So they give you exact answers to the wrong problem. But if their problem is close to your problem, then they become approximate answers to the right problem. That's the way the variational thing works. And the problem with that, as I said, is that they're never able to really tell you quite clearly how close their problem was to your problem. They can always guarantee that the problem they solve for you is the closest possible to your problem in the space of problems that they know how to solve quickly, but they don't tell you how big that distance is. So yes, you got the closest problem to the one that is yours, but it still might be a mile away, and all the other ones were 7 miles away. It's like that. So that's the problem with the variational approach. But they have shown when they run the variational approach on data sets that were small enough to be able to do MCMC on it, that there is a certain set of problems for which the variational stuff does a good approximation in small and moderate sized samples, so then you can probably trust it in large samples as well. I will give you a different approach to approximate large database later on. I'd like to tell you the history behind this. Metropolis and Ulam were not allowed to publish that insight, even though they developed it around the year 1942. They were not allowed to publish it until 1949. Why might that be? It was a government secret. They were working at Los Alamos. They were working on the Manhattan Project, and it was a government secret. Metropolis, working with a number of other people, and the people called et al. Here, were not able to publish their algorithm based on the Metropolis Ulam insight until 1953. And again, they developed this algorithm around the year 1943. So there was a 10-year moratorium on this from the government. But the crucial algorithm that shows Bayesians how to make highly accurate approximate computations for small and medium-sized data sets was available in the open literature in 1953. And precisely no Bayesians in the world paid any attention to this paper at all. The Metropolis et al. Paper in 1953 was ignored completely by the statistics community. And that was because it was published in the chemical physics literature, and the problem they were solving was a problem about approximating integrals that are just like Bayesian integrals, but they arise in the computation of potential functions. Integrating over potential functions to figure out what configurations of molecules they can create that packs them the closest together. And so even if you had Google Scholar in those days, in 1953, and you could search around for problems that solved the Bayesian integration problem, you wouldn't have found this paper because it's not couched in Bayesian integration language. What we actually need, because of that, I will guarantee you, by the way, that whatever problem you're working on right now, there are 5 to 10 papers written by people in some other field than the one that you know that are somewhere between moderately useful to highly useful, ranging from up to highly useful for you, and you just don't know about them because you haven't read those literatures. Whatever your problem is, I guarantee that to be true. There's so much stuff that people are doing in allied fields. And so what that means is that what we really need is not Google Scholar, which is a great thing to have, but we need something that I could call a kind of similarity engine that would work like this. I tell the similarity engine, please go out and find all the papers that solve a problem that's like the following problem. And then I specify what I mean by the word like. And if I do that right, then I can make Google Scholar really behave more like this. Let's call it an analogy engine. I'm creating an analogy between one class of problems and another. Please, Google Scholar analogy engine, would you please find for me all the papers that solve problems that are like this problem here? Did he? Oh, yes, with variational. Yes, he did. Yes, he did. Although, as usual, the devil's in the details about the meaning of the word like. And specifying like is an NP-hard problem, right? But that no one knows how to do that yet. And so we can't build a robot like this yet. But
right? So if I'm working in discrete space and I have a problem and it generates a sequence of integers,
yes,
I can type it into the integer sequence online database, and out come all the problems that generated that particular sequence.
That's cool. I didn't know about that. That's a very small realm in which someone's already built the analogy engine.
It's been there for over 12 years.
That's great. That's great. Okay, so that's the problem. We didn't have an analogy engine in 1953 either, and so no one in the statistics community knew a damn thing about these papers. Then comes along 1970, and a statistician, a good one, named Hastings, a Canadian statistician, published a paper in the journal Biometrica, which is one of the top research journals in statistics, in which he showed how to generalize the Metropolis algorithm, the one that was published in 1953, to work even better than Metropolis's algorithm did. Again, Bayesian statisticians paid no attention to Hastings' paper at all, because once again, it was written in the language of chemical physics, and he was still talking about potential functions. And he was not a Bayesian, Hastings, and he didn't know that he had solved the Bayesian integration problem. He didn't write his paper that way. So now the Tower of Babel problem is even worse than you thought, because now someone's writing in the statistics literature how to solve your Bayesian integrals, and no one notices it because he didn't write the paper from a Bayesian perspective. Then in the early 1980s, these two applied mathematicians who were brothers, Sid and somebody else, Gehman, I forget, Donald maybe, Gehman, who are writing from the applied mathematics perspective, they independently rediscover a special case of the Metropolis-Hastings algorithm. And they call it Gibbs sampling in honor of the physicist Wilford Gibbs, I think was his name, or Willard Gibbs, back around the early 1900s. And this turns out to completely solve the Bayesian computation problem, and they even write about it in a way that shows that they're approximating Bayesian integrals using this method. However, they didn't publish it in the statistics journal. They published it in the IEEE transactions. And not very many statisticians read the IEEE transactions. So it was only finally toward the end of the 1980s when there was some conference called in which the Gaiman people got together with some statisticians, and they told them that the statisticians all moaned about having these terrible integrals, these Bayes, and Gaiman said, we solved that for you back in 1982. Just look up our paper on Gibbs sampling. And then finally the penny dropped. And that turned out to coincidentally be the same moment in history approximately when desktop computers of the kind people could buy and put in their office got fast enough that you could run Gibbs samplers overnight. And Adrian Smith, who was one of the early guys who promoted this, said, you could do it during the day too, and it'll be a nice Bayesian thing to do, because Bayesians always get together on their conferences at places with nice beaches, and it's all about recreation along with the talks. And Adrian Smith said, start your Gibbs sampler at 9 o'clock and go to the beach, 9 a.m. and go to the beach. Come back at 4 o'clock and you've got some answers. So that was his solution. And then people noticed that actually all they were doing was just reinventing Metropolis Hastings over again. And so now we have a very broad ensemble of Markov chain-based methods, and even things that are generalizations away from Markov chains. But the whole idea comes down to learning about a high-dimensional posterior distribution by sampling from it. And so that's what this unit is going to be about. And the reason that Metropolis and his colleagues wrote about these papers when they did was they, in effect, wrote papers that were 30 or 40 years ahead of their time because there were no computing facilities available to actually implement the algorithms. But they knew that computing was coming because they were in direct communication with Alan Turing and the people in the Bletchley project that was cracking the German Enigma codes. And Alan Turing wrote to them and said, don't worry, I'm building a computer now. And he built the world's first analog computer as part of cracking the German Enigma codes. And so Metropolis and Ulam knew that fast computing machines were not far away because Turing had shown them how to do it, both in terms of the theory of building such a machine. As you know, he was the father of computer science, and also with respect to how to actually do it physically with vacuum tubes in the case of his analog machine, and of course transistors with respect to the digital machines. And so here, what a beautiful idea. They published a paper that was 40 years ahead of its time, but they knew that the time was coming because computers just had to get fast enough to make it work. And they also had to wait for statisticians to bother to stumble over it and then make it better. So that's the story behind MCMC, and when we convene next time, we'll spend probably the whole 6 hours talking about how to do it and giving some practical examples of actually doing it using MCMC software. So video guys, that concludes today's presentations, and you can shut down the video now. I'm going to turn off the audio.